So that's kind of wraps up what I have to talk about. The next guy to talk is Mark Lucovsky, and he's going to talk about the Win32 base APIs. Do the slide, okay?
Yeah, if you want to give them to her, I'll have Madeline do it.
All right. This is the set of slides.
Okay.
All right. This is not. No.
Okay. Do you want to hang on to those, or do you want me to hang on to all of them so you get to go through that?
You can.
We're going to talk about the Win32 base APIs, but I can also cover any kind of questions you guys have about POSIX and the whole POSIX server issues. I don't have any slides on that, but I did a lot of the original work, and if you want to understand anything about it, let me know. The base API includes all the low-level operating system functions needed by GUI apps. It's basically all APIs not associated with window management or graphics are part of the base API. This includes tasking, process and thread APIs, memory management, synchronization, I/O, and other miscellaneous APIs, some holdovers from Win16. The base is implemented mostly as a stateless DLL or shared library directly on top of NT. There's very, very little of the base implemented in the server. Picture that in just a second. But where there's state that's shared between multiple processes, the Windows server takes care of those APIs. And finally, the API set is based in its entirety on the Win16 base API. There are a few things taken from OS2 and LAN Manager, like name pipes and mail slots and some of the async I/O, but basically it's an extended Win16 with a few of the networking extensions. Structurally, it's pretty simple. There's the Win32 application program, and it makes all Win32 calls by calling into the Win32 DLL, and this is just a standard procedure call interface. Then from there, the Win32 DLL exports base, user, GDI, and the console API. So all Win32 APIs are bound into here. Once they get into the Win32, yeah. GDI is the graphics. I don't know what the D and the I stand for.
Device interface.
Graphics device interface. And user is the window manager. So there's base, which is the traditional operating system sort of functions, and then the window management functions, and then the graphics functions like line drawing and that sort of thing.
So in general, you refer to your window manager as the window system as a user?
Yeah, it's called user.
I'll talk more about that.
Scott will talk about user later on, and then there's going to be another presentation on GDI. But anyway, so all Win32 APIs are exported up here. Once they get into the DLL, there's basically three types of APIs. There's APIs that are done entirely in the DLL, in which case you're just making a procedure call, the DLL is doing a little work, and then returning information. And examples of that are Win16 has this concept of a local atom where you can store a string and refer to it using a 32-bit handle, basically. So that's all local state that only affects your process. It's not shared anywhere, so it's done in the DLL. This DLL has some memory associated with it that when you bind to the DLL, you map the code and data into your address space, and that data is private to your address space. It's actually shared read-only, copy on write. So for the read-only portions of it, it's shared among all Windows users. And once you touch it, you get a private copy of it. So there's a large set of APIs that are done entirely in the Win32 without calling into NT for anything. Then there's the sort of APIs that are implemented by the DLL, massaging parameters and then calling NT. Examples of that are things like opening a file or reading and writing a file or allocating memory or some of these other sorts of things where Win32 just puts a user-friendly interface on top of the NT APIs and gives it the Windows look and feel without changing any of the underlying NT functions. The third class of APIs are those that are done in the Win32 server. And these APIs are done in the server because they create global state or effect global state. And examples of that are Windows has this global memory heap. It's called global alloc with the DDE share option. But what it is you can essentially malloc a piece of memory, and that memory is visible in all Windows applications at the same address. So the Win32 server maintains the heap structure for that pool of memory.
What's that used for?
What's that? It's used for some message passing, but you can use it for general shared memory if you want to. It's kind of weird shared memory where the sharers don't have to agree to share. It's really global memory, and you can allocate a piece of it. So
I'm just wondering how it fits into the security.
Well, it fits into Windows. That's how it fits in. Yeah. No, there really is security on Windows. The Win32 servers does enforce security. So in this DDE pool of memory, there's actually multiple pools of DDE memory. So when one desktop is logged in under Fred and all the applications started by Fred have a pool of DDE memory. So your logon index will tell you which chunk of DDE memory you get to share with all your other apps. And then there are some facilities for transferring between the two through a special clipboard option or something. I don't know. Anyway, so other APIs that are done like that are the console API and a lot of the window management and graphics. That class of APIs are done by calling into the NT executive and doing an LPC remote procedure call over to the Win32 server. So what happens is the application calls into the DLL. The DLL marshals the arguments into a piece of memory shared between the application and the server, and then calls the server with an API number and pointed to the shared memory. The server then does the API and replies back through the LPC port. For the base, it's like there's maybe 4 APIs that are done in the Win32 server, and the other 100 and some odd APIs are done entirely in the Win32 DLL. So that kind of gives you a feeling for how much you can really do in these DLLs and how little you actually go to the server for that sort of thing. For user and GDI, it's a different story because most of what they do is affect global state, like flipping regions and windows and that sort of thing. POSIX is real similar in structure to Win32, where you basically have your POSIX app and your POSIX DLL and then the POSIX server. The difference there is that just a much higher percentage of the POSIX APIs have to be implemented in the server because there's so much global stuff going on, like Signal. Signal says, geez, I want to throw something on the stack of another process. And there's all these rules about geez, are you in the same job control group, and does your PID match somebody else, and are you a zombie, and all that stuff. So the entire POSIX process structuring and relationships are implemented in the POSIX server, and any API that has to take a look at that structure is done in the server. But things like I/O, or at least I/O to files, are done entirely in the DLL. I/O to pipes is done in the server because again there's global state that's being affected, and there's all sorts of rules about buffer full, buffer half empty conditions and that sort of thing. But basically it's real similar in structure to 132. So when we came up with the base API, our primary design constraint was that we wanted to provide an API that allowed simple migration from Win16 to Win32. So the API looks and feels like Win16, and to most apps it can really be viewed as a wide version of Win16. There's not a lot of random changes just because we were coming up with a 32-bit API. So the APIs have been preserved but widened. And we believe that you're able to share common code between the 16-bit code and the 32-bit code, where your pointers in 16-bit lab will automatically be expanded to 32-bit, and you won't really have to think a lot about it when you're talking about the base APIs. Unlike Win16, the Win32 base API is a complete API. In Win16, if you wanted to open a file or do, create a directory or something like that, you actually had to do an int21 to call DOS to do that operation. So Win32, given that it was going to run on non-DOS platforms, we ended up, having a formal create directory, open file, delete file API set, so that they could write a portable app and you don't have to rely on DOS. And that also lets us run on RISC and it lets us run on DOS and NT equally well. The API includes advanced features like the true 32-bit memory management, threads, map files, asynchronous I/O, synchronization, security, and exception handling. We also added long file name support to the API. So we don't limit anybody to the 8.3 DOS semantics, even though on DOS the applications are going to tend to run into fat file systems, where the file system is still going to enforce an 8.3 structure, but as far as the API is concerned, it'll run equally well on long file names capable file systems like HPFS or some of the other ones being built right now. We also exposed the 64-bit file pointers in the base API. So where the original Win16 set file pointer thing looked a lot like a Unix LC, we kept that same idea but added an optional pointer to the second half of the 64-bit seek position. So you could choose to use 32-bit file offsets and not restructure a lot of your code, but you could also use the 64-bit file pointers if you wanted to convert over to that real easily. The only other thing is for Win32, since it does have security, it's enabled when it runs on NT, but it's not functional when it runs on DOS. So the security parameters are ignored. The biggest change for the Win32 process model is that it allows multiple threads per process, and it has preemptive scheduling. In Win16, you could only get rescheduled when you called to pull for window messages or actually called to yield the processor, but on Win32 it's fully preemptive, just like the underlying NT system. All threads are peers. Within a process, they can all see all of the objects and open files and semaphores that the process can see. They can also all create windows or do graphics or call any base API. So there's not a special thread, like in OS2 thread 1 is special because if it dies, the process dies, and it's the only one that sees signals, but in Windows they're all peers. Again, scheduling is preemptive. We also have priority control. Processes can attach to DLLs either statically by, the image is actually linked to a DLL, or at runtime they can call an API to load a DLL and look up procedure entry points in the DLL. DLLs are given a chance to initialize. Whenever a process loads a DLL, we call an init routine in the DLL, and when the process unloads the DLL, we also call termination routine inside the DLL. Win32 exports structured exception handling that Dave already talked about. That's made public in this API. You can use this, the same way you use it under NT to catch exceptions and recover from errors or touching bad memory, doing your own pagers or whatever it is you want to do. The other thing that we've done here is all threads have a single.
Excuse me. How's that supported on the low end of the DOS?
What? Structured exception handling? Well, it's not really. I mean, it's supported the same way it is on the high end. It's built in. It's built into Win32 on DOS. Win32 on DOS is a real operating system that really takes control of interrupt vectors and the exception handling stuff. So it's all there. Windows on DOS isn't like you can't just party on DOS like you can if you're not running on Windows. So you can't just go in and say, I'm going to take over this interrupt vector and not let the operating system see it. If you did that today on Win3 or Win3 not running in enhanced mode, you could crash Windows and you can cause Windows to hang. So it is a real operating system. You can't just think around like you could on DOS. Each thread has a single 32-bit last error word. So when you call an API that fails, this word is updated with the error status and you can call to get extended error information. So if you're looking at a multi-threaded app where they're all doing things, we don't have the errno sort of problem where errno you might have failed, but somebody else had just cleared errno from a previous call. So we have this get last error API that when you fail an API, if you care about the reason that you failed, you can call get last error and get the information. Otherwise, you can just key off of the failing API and just ignore the fact that you updated this cell.
The failing API doesn't raise an exception with you. Right?
No.
Doesn't have that.
Well, it depends on how the API fails. And like if you're doing an API that's done entirely in the DLL and you pass it a bad pointer, you may or may not get an exception as a result of that bad pointer. It depends on the API. We're not going through the trouble and saying, hey, all pointers are going to result in an error of type access violation. You might see an exception as a result of passing a bad pointer. Just like if that API happened to be implemented in a C runtime, you would probably get an exception or get a core num message rather than anything else. So I think that we're being semi-consistent that we're not raising exceptions always and we're not returning errors always. It depends on the API and whether it has to catch an exception so that it can clean up some stuff that it's halfway started. It'll catch the exception and you see the error as an error result code. If it doesn't have to do any cleanup and it's safe for it to take the exception and pass it on up to the caller, it'll do that. So it's not.
Did you go and change any of the things that were in the Win16 API to add exception? Do any of the functions that were in the Win16 API that didn't raise exceptions, do they now raise exceptions?
They can. What
You
is
pass in a
Windows?
bad pointer, certainly, but under enhanced mode, you would get the same thing. a default, wouldn't be an exception you could actually handle.
Yeah, it would be something that would just kill the app, right? So, you know, I think we're being consistent in that at least, you know, we're giving you a shot at it. And in fact, before each thread starts, there is Win32 establishes a default handler at the top of each thread. So exceptions are always going to be handled by either the Windows frame-based handler, or Dave mentioned the exception port that's a per process port. If you've completely destroyed your stack or any of the frame-based handler tables, Windows will see the exception through the exception port and cleanly terminate the application or keep it going, depending on what's appropriate for that sort of exception. The most significant change for Win32, of course, is the 32-bit flat address space, whereas all previous Microsoft systems were 16-bit segmented. This is the first 32-bit version of Windows. Memory is addressed using flat 32-bit addresses. This gives apps and DLLs access to 2 gigabytes of address space. Dave mentioned that we try to position the DLLs, the system DLLs at least, in an area where they're not likely to conflict. What we're doing today is putting them at 1.5 gigabytes. We're starting our system DLLs there and going upward, but that's just out of convenience. We could go at the top and go downwards, but we're trying to cluster them up at the top end of the address space today to leave the bottom open for things like Windows. Another thing that we're doing is as a default, we base user mode images at 4 megabytes. That gives people that are doing DOS emulations on top of Windows, it gives them the first megabyte to do the DOS emulation work. And so 32-bit Windows apps aren't going to collide with a DOS emulator that wants to be down at a megabyte. The memory management API is very, very similar to NT, and that it allows sparse sparse allocation with reservation and commitment. It gives you control over a page's protection. Where NT lets you set, half a dozen or a dozen different page protection fields, Windows lets you set a page to read-write, read-only, or no access. So it doesn't support or require all the copy on write variations and execute read, execute write variations that NT has. So it's a subset of NT, and it's also presented a little bit easier.
It's a nice coincidence.
Huh?
It's a nice coincidence
What's that?
that NT and Windows have the same memory management model.
Yeah, isn't that interesting? Well, OS2 has a real similar model here too, and it's a real natural model. The thing that NT does that's a little bit different than all the other systems is the memory management APIs all take a handle to a process. So you can allocate and deallocate and change page protections in another process, and that's real foreign to a lot of operating systems. Even Unix doesn't have anything like that. But NT has this process handle associated with memory management APIs, so that from a server process you can affect a client's address space. So for the way that we do pipes on POSIX today is all the buffering logic and the actual pipe buffers are done in the server, and when you do a read or write that happens to go to a pipe, we go over to the server process, figure out the new pointers for the pipe, and do either a read or write virtual memory API directly into the other guy's address space. So we don't actually slosh data around through some LPC thing where you have to copy it twice. We just say, hey, I want you to copy this memory into that process at this other address. So that's the thing that's unique about the NT API is that it really is geared towards allowing these servers to have full control over their clients. Win32 supports a stripped down version of the memory map files that are present in NT. And by stripped down, it basically doesn't have the option to let you map a file as if it were an image. You know, through the public API, you can map a file as a data file. We don't have the bit that says parse this thing as an image and expand it into my address space. That's something that applications tend to not have to do. It's more things like system loaders and system software wants to do. We want the Win32 API to be widely implementable, and that's one thing that could restrict guys a little bit. The other significant change from Win16 is that Win32 runs each process in its own separate address space, where under Win16 they all ran in the same address space. So all memory was essentially global memory. Win16 has a few different heap managers. They have local alloc, which basically lets you do memory allocation and movement and that sort of thing within a single segment. Global alloc, which lets you allocate and free memory that isn't bounded in a 64K region. Win32 implements both of these APIs, and they're fully compatible with the 16-bit versions. Only they're not, local alloc isn't constrained to the 64K region. So they're really there for compatibility, but the distinction between what the two API sets are for has changed because of the 32-bit addressing. We also added a new set of heap APIs that take a heap handle, so you can create a heap and then do allocate some frees that are based on heap pointer if you want. If you think that'll help your app. What you could previously do in Win16 is to get multiple heaps was change the value of your data segment and call local alloc again because it was just allocating out of your DS. So we formalized that concept with the new heap APIs that reduce the functionality from what you can do with local alloc. Win32 has a full set of synchronization primitives. It has the critical section, which is the fastest possible mutual exclusion object. It's for threads within a process. It's not a shareable sort of object. It's basically it's like an OS2 fast safe RAM semaphore, which is an in-memory test and set sort of thing, where if you get a collision, you make a system call to wait on a semaphore. So in the absence of contention, you can go in and out of these things in microseconds rather than having to call the system. But the downside is they're not shareable. We have the mutex, which is basically a shareable version of the critical section. But both of these are also recursive. We have event objects that may be shared. They can either be automatically resetting or manually resetting. And then there's counting semaphores. There's also a generic wait operation that you can wait on a single object or any or all of a set of multiple objects. You can also wait on process and thread objects, and those objects, waits on those are satisfied when the process or thread terminates. So the way you would do a C runtime sort of system API is you create the process, and then wait on the handle that you got back, and when the wait was satisfied, the process is exited, and then you can exit code using another API. Then when you're all done with that, you can finally close the handle to the process. These are obviously all ND safe. Better sound support is new in Win32. We've added a full 32-bit version of the full multimedia Windows sound APIs. This includes sampled sound, record and playback, and a MIDI sequencer. Sampled sound and MIDI sequences can also be transmitted through the clipboard and DVE and stored as resources. So you can store in your file, clips of sound. As a resource. That's another example of what Dave was talking about when he talked about resources. So I guess to summarize this, Win32 is simply a stretched version of Win16, overcoming some of the shortcomings of Win16 by adding things like threads, address space separation, security, long file names, and just kind of the general clean up and flushing out the API to make it a real portable API that isn't relying on DOS for everything it does. So that's all I have to say. I think Scott was going to talk about the window manager next, unless there's any questions about how to cut systems.
What's the NT instruction that for the sound back to?
Well, the NT sound stuff is done in the is a sound device driver. So I don't know if it's high octals to do certain things, but the read and write is the way that you pass data to it. And I don't know if the data is interpreted or not. I think that's...
Can we get copies of your slides?
Yeah.
I have 10 copies there, so if I need to bring more
That's enough
copies.
of 7 visitors here, so.